Okay, in this video I'm going to continue on with exercise 5C of the book Fundamental Applied Mathematics. We're on page 139 and the question is 5. It reads, a particle of mass 3 kilos is held on a smooth plane which is inclined with a slope of 1 in 3. That is to say, the sine of A is equals 1 over 3. It is connected by means of a light, inextensible string passing over a smooth pulley at the top of the plane to a particle of mass 10 kilos which hangs freely. Find the common acceleration of the particles and the tension in the string after the system is released from rest. Now, this question is different from others we've done so far, because in others we're either dealing with the x, y plane or the x prime, y prime plane, and there hasn't been a mix with both, or it's been pretty obvious which one we choose. However, in this case, we can see that the 10 kilo mass is in the x, y plane, so we'll say there's my y axis, there's my x axis, and there's my y prime axis, there's my x prime axis. So we can see we could analyse the motion of the 10 kilo mass perfectly in the xy plane. Similarly, we can analyse the motion of the 3 kilo mass in the x prime y prime plane. Alright? So how do we do it? What's the best way to go about doing this? So what I say is whatever I would say frame of reference makes the majority of the analysis easier, go for that. And in this case, we have to resolve if we resolve the 3 kilo mass, the weight of it, into the x prime y prime axis, well then the analysis of this is pretty straightforward. And that means, for that reason, I'm going to actually have to put the 10 kilo mass into the x prime y prime plane rather than the x y plane. So first of all, note of course that the sine is 1/3, therefore the cosine is √8 over 3. I've drawn my unit vectors incorrectly there, in fact, because as I said, I'm going to go for the unit vectors being parallel to the x prime y prime plane, like so. And the gravity vector hasn't changed, and that means that it's not j hat there like that. So let's go about doing this. Let's resolve the the weight vector, excuse me, of the 3 kilo mass. So we go parallel to the y prime, parallel to the x prime, put them at right angles, and they must be in these directions there. So similarly, we need to do it for the 10 kilo mass, the weight of that. So we go parallel to the y, parallel to the x, put them in right angles, and they must be in these directions here, like so. What about the tensional vector? Let's put in the tensional vector. So we have a tensional vector here and a tensional vector here. They're both of the same magnitude, and the only reason they are of the same magnitude is because the string is massless. We notice this tensional vector is in the x prime y prime plane perfectly. However, this tensional vector here is not. So we need to resolve that vector. So we're going to go parallel with the y, parallel with the x, put them at right angles, and put them going in these directions there. So they must go that direction in order to add together to create the create the vector t. So for that reason, I'm just going to get rid of these now because we don't really need those. They're just cluttering up the diagram at the very least. So what we have here is, we'll say w sub x I hat, and it's actually in the negative I direction. This is negative w sub y in the j hat direction. This is positive t sub x in the I hat, and this is t sub y in the j hat. This is, I'm going to call it negative w1 sub x j hat. This is negative w1 sub y j hat, like so. And everything else is pretty good. So let's start applying Newton's second law. So remember, we're either going to deal with 3 kilo mass and then the 10 kilo, or the 10 kilo and then the 3 kilo. Alright? So it's pretty straightforward stuff. So let's first of all go about calculating the magnitudes of our tensional and our weight vectors. Alright? So let's look at the W1 is equal to negative W1. Now, let's look at the angles here. This one here is A. We spoke about why it is in the past. That means that this vector here is also A. Now why is it A? Because, well, if you look at minus wy sub j, it's actually perpendicular to the x prime axis. Alright? So that means its angle is also equal to A. Similarly down here, this angle is equal to A. Alright? So we just got to be smart when we're applying our trigonometric functions. So W1 is here. So we get W1 times the cosine of A, and that's in the I hat direction, and take away from that W, oh wait, sorry, I did that wrong. W1 times the sine of A in the I hat, and you take away from that W1 times the cosine of A in the J. And it's going to be, over here, it's going to be W, and it's going to be negative W times, now this is going to be the sine of A in the I hat, and you're going to have to take away from that W times the cosine of A in the J hat direction. And finally then we're going to look at the tensional vector up here. So it's going to be T is equal to, it's going to be, now it's A, it's opposite here, so that's going to be sine. So we're going to go T times the sine of A in the I hat direction plus T times the cosine of A in the J. Alright, now notice the signs. These ones here, of course, are going in the unit vector directions. These are opposite to the unit vector, and so are these. Alright, so that's pretty straightforward stuff. Now, can we put in any of the values which you know? Do we know any of these values? Okay, so let's look at W1. Well, this is 3G. So is this. W is equal to 10G. So is this. And we don't know what the tensional vector is because we're trying to find it. We know that the sine is a third. That means this is the sine of a third. So we know this is a third here. And the cosine is root 8 over 3. Root 8 over 3. And we know the cosine here is also root 8 over 3. Alright? So we're not doing too badly so far. Let's just put in these values. We know that the cosine was root 8 over 3 here, and we know that the sine is equal to 1 over 3. Alright? So now we need to apply Newton's second law to all these different systems. So I'm going to start off with the 3 kilo mass. So we know from Newton's second law, and I'm going to do this in green, that the sum of the forces is equal to the mass times the acceleration, and these are vectors. So let's just do this in the x direction, or the y direction first, right? So the sum of the forces in the y direction is equal to n j hat, and we need to take away from that, w1 sub yj hat, which was here, so that's equal to, it's equal to root 8g j hat. That's equal to the mass, which was 3 times its acceleration. Now we know, of course, that this block isn't going to lift off the x-axis or the x prime axis, so there's no acceleration in that direction. So you know that the normal vector is root 8 times g. All right, root 8 times g. So we can say this is equal to root 8 g j hat, like so. All right, that's pretty straightforward. Now let's apply the same to the x dimension. So we know that the tensional force in the I hat direction, we need to take away from that g, because 3g times a third is g, is equal to the mass, which was 3 times the acceleration. Alright, now let's look at the acceleration of the whole system. Will it change? Will the acceleration of this mass be different from this? And the answer is it won't, because they are both on the same rope. So we can say we have negative a j hat here, and we can't actually, that's incorrect, we can't. So we'll say this here, sorry, is a I hat, and now this, if it's going down this direction here, right, its magnitude is a, but we need to resolve this vector once again into its component. So if this way, this is going to be a times the cosine of a j hat, and this is going to be a times the sine of capital A I hat. Alright, this angle here is a for the exact same reason as we've had in the past. And we didn't have to do it over here because this is moving, it's in the x prime dimension, or the I hat unit vector direction. So anyway, we're applying it down here. Alright, we're applying it down here. So what do we have? We have 3 times a, that's fine. And we just call this equation 1. So I'm just going to write this in the corner. T minus g is equal to 3a. I'm going to call that equation 1. Alright, so that's pretty straightforward. Now let's do the similar analysis to the 10 kilo mass. And let's talk about the j direction first. Alright, so we have the following. We have t sub y j hat. So t sub y j hat is equal to t times root 8 over 3 j hat. We need to take away from that the, what else do we need to take away from that? This one here, minus w sub y j hat, which is here. So that was equal to minus 10 root 8 g over 3. And we need to multiply that by the mass, which is 10 times the acceleration vector. Now look, the acceleration vector is going to be in the negative j. So it's going to be a negative times a, and the cos of capital A was equal to root 8 over 3. Alright, I'm actually going to draw that negative sign in red just so we can see that. Alright, so let's just rearrange this. I know it's looking pretty complicated, but it's not too bad. So of course we can cancel 3 everywhere, and we can cancel the root 8 everywhere because they don't matter. So we're just going to get t minus 10g is equal to negative 10a. So equation 2 is going to be t minus 10g is equal to negative 10a. Alright, so that was pretty straightforward. And finally, let's do the exact same thing for the 10 kilomass, but in the I hat direction. Alright, so we have the following. We have t sub x I hat, so that's down here, so that's t over 3. Alright, we need to take away from that w minus w sub x I hat, which was here, so that's equal to 10g over 3. We need to multiply that by the mass, which is 10, and the acceleration. The acceleration in this direction is going to be equal, that's incorrect there, that should be this way. So it's going to be a negative number again, it's going to be a, and the sign of it is equal to 1 over 3, like so. So of course we can get rid of the 3's across the board. We get t minus 10g is equal to minus 10a. We get the exact same equations here. T minus 10g is equal to minus 10a. We've got the same equation twice, so that's a good thing. That shows we're doing the correct analysis. So let's just finally finish off this. Okay, so let's just finish off this. I know it's getting a bit complicated, but we're doing well. Alright, so we have 2 unknowns, but we have 2 equations. That means we're able to solve it. So let's get rid of this because that's just a copy. So what if we add, we take 1 from 2, or 2 from 1, 2 minus 1, or minus 2 plus 1, sorry. So that's going to be t minus g is equal to 3a, and you're going to have minus t plus 10g is equal to 10a. So we're going to get 9g is equal to 13a, therefore a is equal to 9g over 13. That's the first thing, and apply that to get t. So we're going to get t minus 9g over 13 is equal to 13. Oh, what am I doing here? T minus g, that's kind of mad now, just excuse that I did that. T minus g is equal to 9g over 13 times 3, so 3 nines are 27, so 27g over 13, therefore t is equal to 27g over 13 plus 13g over 13. Alright, so t is equal to, what's that, 40, that is 40, isn't it? So 40g over 13, and a is equal to 9g over 13. Alright, so of course the next thing we need to do is move to the back of the book. So we have 5C question 5. 5C question 5. So 9g over 13 and 40g over 13 are correct. Okay, so thanks for watching. Please pass it on to your friends and subscribe to my channel.